Hello, everybody, and welcome to this month's Footsteps to Mars Hangout. I want to welcome you back after our, I guess it was an unplanned hiatus back in October with that pesky hurricane that caused me to have to reschedule our Hangout for this month. And so our guests were kind enough to be flexible and join us here this month because we're going to be talking about water on Mars, the history of Mars, the history of the study of water on Mars, and we're going to learn about how important it is for our efforts to get us there as well. So we've got a couple of really great guests for you today. We've got Ali Bramson and Jonathan Bapst. These are both PhD students from University of Arizona who've been studying this stuff, and they're going to give us their insights into the water on Mars. And because this is a hangout on air, I need to let you guys know a couple of things. First of all, these hangouts, this whole series, is endorsed by two really great organizations, the American Astronomical Society and the American Astronautical Society, both of whom use these hangouts to highlight their membership and the work being done by their membership within whatever, a variety of different topics. In this case, we're talking about Mars and our exploration of Mars. So, and while they are endorsed by these hangouts are endorsed by these organizations, they are not necessarily, the views and opinions expressed herein are not necessarily endorsed by these guys. So I just wanted to clarify that before we got too far along. Also, but this is a social media event. We hope you guys will interact with us, and there's two big ways to do it. The first one is to go down here to deepastronomy.com/live, and we'll have a live chat client going now. Some of you were already signing in, so that's really good. And so you ask your questions there. I'm also monitoring the hashtag Footsteps to Mars on Twitter, and I've got that on my tweet deck right now. So if you have any questions or comments, you can interact with us that way. So we'll go ahead and get started. Joining me, as he does every week, or every month, I should say, for this hangout, is Dr. Harley Thronson. And you know what we never do, and I remember to do it this time. We actually have a mascot, so you have to show him our mascot.
Oh, the mascot.
You guys may remember during the gravitational wave hangout, we had our rubber ducky. This is our mascot. This is now our water on Mars.
We'll make a connection between the mascot and water on Mars.
But I promise we won't work too hard.
That's part of a challenge for Ali and John.
Right, we'll work it in. All right, so Harley, why don't you go ahead and give us a brief intro into what we're going to be talking about here?
Exactly. This series now, we are actually getting close to, we are approaching almost a year of these Footsteps to Mars. And
is it really? Wow.
Yeah. From whether you're talking from a purely scientific exploration of Mars, which will be our emphasis today, or one day human exploration of Mars, water is a centerpiece. Water is a keystone. NASA introduced, I think it is at least 15 years ago, program formally and informally called Follow the Water, because water is essential to, we believe, the current existence of, possible existence of life currently or in its past. Also, where water might be found on Mars may be really important if humans are one day to travel on Mars. So much of the scientific investigations into Mars, again, as we'll hear about today, and the planning, early days, for humans to travel to Mars has at its core whether or not there is or has been accessible water in some form or another on Mars. So we thought it's time to bring some Martians, Mars scientists, on board our Footsteps to Mars that will specifically emphasize the current understanding of water, where it's located, what form it's in, and something about, so far as we know it, what the history of water has been on Mars and what it tells us about the possibility of life, that sort of thing. So how does that sound?
Sounds great. Thank you, Harley. Okay, so let's go ahead and get started. Let me start with Jonathan Bapst. So why don't you guys, when I pull you up, go ahead and just introduce yourself and tell us what you're studying at the University of Arizona. So first up is Jon Bapst. I almost called you Dr. Jon Bapst, but soon that will be true. Almost there. Go ahead.
So at University of Arizona, I'm studying these ice deposits that exist in the northern polar region of Mars. We call them ice mounds, but they're just these exposed, basically mounds of ice that are on the surface. And we're trying to look at them and maybe understand what kind of climate implications they may hold.
And how big are these ice mounds?
So they can span, I think the smallest one is about 10 kilometers kind of in diameter. It's roughly circular. And then they can get quite large, up to 50 or 60 kilometers in diameter, and a couple of kilometers thick as well. Awesome. So these are large mounds of ice.
Okay, and also with me is Ali Bramson. We couldn't get her lower third up, so I'm going to be saying her name a lot. Ali Bramson, also at the University of Arizona. Do you guys work together, Ali?
Yeah, so we're in the same research group, and we call ourselves Ice Pig. It's an acronym, of course.
Ice Pig?
Yeah, it's like Ice Crustal Exploration and Process Investigation Group. So we both, work on the current ice distribution on Mars and the implications of that for Mars's climate change.
All right, I want to get into some of these details here in just a bit, but you're not necessarily working on the same ice mounds. Are you doing something a little bit different, or?
Yeah, so I look at lower latitudes. I'm mostly looking in the mid-latitudes of Mars. And so when Mars undergoes these oscillations in its obliquity, so the planet's tilt is changing, and that dictates where the ice is stable. And so in some of the climates, ice is more stable at lower latitudes rather than at the poles. And so I'm looking for ice sheets buried in the mid-latitudes that could represent past climates when that ice could have been deposited and then subsequently buried and protected to the current day.
Wow. Okay. Well, so welcome to both of you. I want to thank you both for taking time out to talk with us about this. I want to start a little bit with the history of water on Mars. Now, we've been looking at Mars, as Harley reminded us in the little preamble before I hit the start broadcast button, since about some of the first images from Mars are how old, Harley? How long have we been looking at Mars?
I'm trying to remember. I think it was, and Jon and Ali would correct me, wasn't it what the Mariner missions in the mid-70s, early to mid-70s?
Were they the first?
These were flyby missions.
Right. Those were the first spacecraft to visit Mars. But they've been observing Mars, of course, from
the ground since forever, right? And so now, back in the early days, there were these, and if you're a fan of old science fiction like I am, you know that some of the covers of these novels had pictures of Mars with canals, and from that, these canals had civilizations and big cities, and it was all this speculation going on about Mars with respect to water. So it's always gotten our imagination. But the first pictures that we ended up getting back from Mariner in the 70s, this was pre-Viking, showed us this really desert, sandy, rocky world. And so I wanted to kind of get you guys to comment a little bit on what were some of the early impressions of water on Mars, going back as far as you care to, and how things might be a little bit different today. And so, Ali, I'll start with you, Ali Brammer. What are some of the past views of water on Mars?
It seems like it has sort of changed. Like the perspective is constantly changing, and so, like you said, there were these very early views that Mars was covered in these canals and super water rich. As we started doing spacecraft exploration of Mars, it started almost looking, okay, it's very deserty, very dry. But then as we kept looking, had more detailed resolution images, then it started emerging that that Mars did used to be very wet, because there was evidence for these valley networks and what looked like sort of flowing river features all over Mars. And so that sort of sparked this idea that there was an early in Mars's history, about 4 billion years ago, that there actually was, there would have had to be a lot of water to form these features. And so right now, the current state of understanding a wet Mars comes in the form of trying to explain how you get those features. And I feel like we're sort of in this in-between zone where we're trying to figure out, okay, was it continuously warm and wet? Wasn't it episodic? Just episodic bursts of either like glacial melt that would form these features, or it seems like, yeah, we're sort of in this in-between period now where we're trying to understand just how warm and wet Mars used to be in the context of explaining all of those features.
Yeah, so here
we know today it's dry.
So here, what I'm pulling up are some of the past observations. It's funny. I just did the search on Schiaparelli, and I came up with all of this. And I'm seeing Elsa Schiaparelli. What is that? But anyway, here's the guy I was looking for was Giovanni Schiaparelli. And what we're looking at here are some of the earliest renderings of a drawing, and I guess it was late 1800s from Schiaparelli, who was using a telescope to look at Mars. And these were some of the details that he saw. And obviously there were lots of these straight lines. Now it's important to realize that his telescope had very low resolving power, and there were probably a lot of details that these, you know, the view of Mars tended to change over time, in large part because of the weather. But you also had these canals here. And so this is sort of where we started looking at Mars and go, wow, look at that. There must be tons of water on Mars if it can carve all of these things out. And so, and then we moved on from that just a little bit, well, not a little bit, a lot, to people like Percival Lowell, who used the observatory down where you guys are in your neck of the woods, down in Tucson, and to sort of go a little bit further with some of these. He tried to examine these canals up closer, and I don't know. I think I don't remember what happened, or I don't remember the context of his research. But of course, there was never. I think he actually went so far as to thinking there were actual people or civilizations on Mars as well. Is that how you remember it, Harley?
As I remember it.
Okay, you weren't around, but am I telling a reasonable story here?
Yes. I mean, I was still in elementary school in 1908. I mean, Percy Lowell is, I think, one of the great eccentric, visionary, remarkable individuals in observational planetary science. And once again, stretching back to my history, I believe that I remember reading that he took Schiaparelli's drawings and speculation and so on and so forth and took them another step further with both broader, deeper speculation and attempts to improve on Schiaparelli's drawings. I want to add here, before it goes too far, that as I remember, that folks, once again, in the 70s and 80s, tried to compare the vastly better satellite observations of Mars with the drawings that Schiaparelli, but especially Lowell, did from Flagstaff, and found, I think, maybe only the grossest features. None of the lines. They were a figment of, I think, probably Mr. Lowell's imagination, wishes, dreams, but almost nothing in the images that you're showing there was found to exist in reality. Something of a pity, but it did generate a lot of interest. Lowell's work did generate a huge amount of interest into in Mars, which probably continues to some extent even today.
Right, and so having this as a starting point, it's easy for Mars to capture a lot of our imagination, which it did. And we now have moved on. Now we've got landers. Now we've got high-resolution orbiters going around the planet. We've got all kinds of stuff. And one of the things that some of them, so for a long time, I think, from the 70s, from Viking to some just prior to some of these orbiters, and I want to have our guest comment on this. What was our view of Mars water, say, from Viking until some of the first rovers or some of the first orbiters that we sent in the 90s and the early part of this 21st century? Jonathan, can you comment on that?
Yeah, can I just ask you to specify, are you talking about the history of water or kind of the present day?
Well, our view of okay, so we've talked a little bit about Schiaparelli and Percival Lowell and how they saw things through their telescopes from Earth, and they made these drawings of canals. And Harley mentioned that we tried to go back later and find evidence of these, not really, and so we haven't really found evidence of these straight lines and these sort of artificial looking canals. But we did send probes out there. We have Mariner, from Mariner to Viking to Pathfinder, all Mars Reconnaissance Orbiter now in orbit. How has our view of Mars sort of gone from that point, from say Viking and Mariner, to the present day as far as our view of water?
Yeah, so I think it's changed quite a bit. I think early on, especially with Lowell's maps and stuff, I think people were excited and thought maybe there might be civilizations. And that, I think, persisted into the 50s for sure. But once Mariner went and was looking at the surface, so I believe the first Mariner flyby might have been, I can't remember the exact number, but it occurred during a major dust storm. So you couldn't even really see the surface of Mars. And then the next one, I think Mariner 9, then saw cratered terrain. So what people were expecting was something more like Earth, and what they saw was something more like the moon. So I think people in general thought that Mars was, in terms of water, was inactive. That essentially if there was a water cycle, it's long since gone. And but that's been fine-tuned, I would say, a bit. So in Viking, I think that was still the consensus view. But as we'll probably talk about, there's been some changes to that. But all in all, we've been basically nailing down the environment of Mars and over these years. And we're finding that it is a very cold and dry place. So it's hard to envision much active water or a lot of water activity today at the surface.
Right, and which is really too bad. But there was some big news just this last year. In fact, I kept hearing these press releases coming out over and over about there's finally evidence of liquid water on Mars. And maybe I'll pull that up. So before we started, you had me go to some of the HiRISE images. And by the way, I put a link to this website in the description box of the video, so you can get these images too. But let me just share my screen real quick and show this. This is some of the more recent evidence of water on Mars. And this came out just last year, didn't it?
This is from 2011. And one more thing I want to note that Ali kind of alluded to earlier is just the improvement in resolution. I think there was a lot of skepticism, especially from the Viking days, because, of course, Viking had high-resolution cameras compared to its predecessors. But those are like hundreds of meters, kilometer kind of pixels in those images. And with HiRISE, which makes up this GIF that we're showing, the resolution can be 25 centimeters per pixel. So
that's a really good point. So yeah, this is from the HiRISE, which stands for, I believe, high resolution imager. And it's what it does is it gives us high resolution images of Mars. And that's a good point. The detectors and cameras have come a long way over the years. And so these are some of the latest ones back in 2011. And what are we looking at here? Let me get Ali into this. So Ali, why don't you describe a little bit what we're looking at here?
So these are features you can see over time throughout the season that you get these dark streaks that are flowing, or not, I shouldn't use the word flowing necessarily, but you see them propagating downhill. And when they get darker and start propagating downhill, corresponds to the time of the year when it would be warmest on those slopes. And then they retreat when it gets cold again.
Okay, so that we can kind of get a sense of what we're looking at with this picture. The downhill is going from right to left in this image, and this graph at the very top left of the image marks when in the Martian year these images were taken.
Yeah, so that LSABS, that's essentially what we use to measure time throughout the year and the seasons. And so they tend to propagate when the slopes are warmest, and then we see them fade away when it gets colder again. And these things, so they're called recurring slope lineae, or RSL is the acronym, and recurring because we've now watched this process happen many times in the same locations, and we keep finding new locations that this process is happening.
Okay, well, let's get to the features that are most striking here. These dark streaks that start appearing. Is that water flowing? What exactly is that?
That's what everyone's still trying to figure out.
So there are these dark features then that are just sort of appearing, and they are on top of light colored sand, it looks like, or lighter colored sand, but nobody knows what these are yet. No one can tell you what they are.
So there has been some spectroscopic evidence that suggests hydrated minerals are associated with these features, and that was what the big press release was last year that garnered a lot of attention, is that there's likely some hydration here, but I think the image that we all want to have in our head, and that the public probably got from the press releases of that, this is just flowing water, I think is a little is maybe a little ambitious. There are some dry hypotheses out there that don't invoke water to try to explain these, but they're still sort of a mystery. I'm not sure.
Okay.
Maybe Jon has some additional comments.
Do you have
on
anything
them.
you want to add to this, Jon?
I would just say that because we understand, or to a point, we understand the environment of Mars pretty well. We know that it's cold. We know what the atmosphere is made of. We know what the pressures are. And so it's hard to really envision liquid water. So if this is liquid water flowing down slope, then you have to include some sort of something to depress the freezing temperature, some sort of salts maybe. And so that's, like Ali was saying, we see these associated with hydrated minerals and salts. And so the thinking there is that
that's a good
those
point,
are
because
depressing
on Earth, fresh water freezes at a higher temperature than salt water does, correct?
Exactly.
So yeah, you need something like that maybe to keep it, if this is in fact flowing water. But it's hard to say because the time resolution is pretty low. So it's hard to say for sure if that's what is actually happening. But there's a lot of things that would affect liquid water, not the least of which is the temperature, but also the fact that there is a very low atmospheric pressure there too, right? So these water flows, if that is what they are, would pretty much evaporate pretty quickly, I would think, right? Because of the atmospheric pressure that's happening there. So, all right, well, so there is beginnings of evidence here that there might be liquid water that flowing on Mars now, but certainly there's evidence geologically that this was probably a lot more common, right? We've all seen the canyons and things like that where that look to be carved out by water. Is that correct?
Yes.
So is the hypothesis then that back in Mars past there was probably a lot more water, correct? What would the conditions of Mars have been like for that to happen? And Jonathan, I'll go ahead and go with you.
Okay. So I think the biggest issue is the one you raised, which is the atmosphere. And that's, of course, connected with the temperature at the surface because of the greenhouse effect. But because the atmosphere is so rare, if you will, at the present, water at least pure water at even low temperatures, just a couple degrees above melting, would boil actually because of, in some parts of Mars, because of how low the total pressure is. So for large amounts of water, to envision those being, eroding the surface, billions of years ago, you would think that the atmosphere had to be much thicker to stabilize large scale bodies of water or rivers or.
Okay. And Ali, let me ask you to add to that a little bit. Are there any ideas or theories as to how much water there might have been on Mars in its geologic past?
I think due to just all the geomorphic evidence, that all suggests that there has to be a lot. You have to get a lot of water to get all this erosion that we see in the form of valley networks. And also there is quite a bit of spectroscopic evidence, and also the rovers have measured clays and different minerals that suggest formation in the presence of water, shallow streams, lakes. And so I think, yeah, there's a lot of evidence that there would have to be a lot of water, but it's still a little bit hard to explain all that water without having a lot thicker of an atmosphere, as Jon mentioned, needing to get higher pressures to make it so that regimes that Mars is at is where water can exist in liquid form and not just ice and gas like it does today, given the low surface pressures.
Okay,
So, I was going to ask one of those sort of curiosity questions, but then a more serious question in response to something that Jonathan said a moment ago. So this is brain challenging things. Jonathan, if one had a small pot of liquid water in your spacecraft on the surface of Mars and you put it out, would it boil before it froze, or vice versa?
It depends where you are, but I think it could happen simultaneously. It could begin boiling, but would freeze at the surface. And so there is this idea that even if Mars never had a very significant atmosphere, you could still somehow maybe envision ways where you can bring water to the surface and it can perform its erosion with like an ice layer essentially at the top where we have water still flowing beneath it. Kind of similar to maybe some lava flows where you...
Oh, interesting.
Yeah.
Then what about, before we leave one topic, before we get deeper into this one topic, we know, of course, or I think it's widely believed that Mars has flipped its axis from time to time. Has that played a role? I mean, so obviously it would play some role, but would that have played a significant role in making water liquid water more or less common on Mars?
I'll let Ali answer that.
Ali?
By flip axis, you mean these oscillations in the obliquity?
Yeah, that first.
Yeah.
And also hasn't Mars actually, or isn't it thought that Mars not only the obliquity, but also the axis flipped like 180 degrees?
Well, you're talking about the spin axis.
The spin axis.
Mars is flipped 180 degrees in spin axis.
Has it? I'm stretching my memory of Mars. I'm a simple astronomer. You guys know.
I don't know.
I know. Of course, it's done.
It precesses probably, but I don't know if it's flipped its lid that way.
I
don't think I've ever heard that. Jon, have you?
I'm gonna. You guys keep talking. I'm going to Wikipedia. They will.
Okay.
Yeah. That would really have an effect. If you can imagine a planet spinning and then suddenly it's spinning this way, that would definitely have a big effect.
I'm trying to like envision
no. Not flipped on its side, but do like tops will do sometimes if you've got the right
precess.
Kind of
so precess. So
no, it's not a precession.
So kind of like a top that slows down, right? Okay.
That is precession. That's not
okay. So your question is, does that have any effect on?
Yeah, Jonathan, you go to Wikipedia while we're having this discussion.
So I mean, the obliquity that oscillates, and it goes through extreme oscillations.
Tell us what obliquity is.
Yeah, so obliquity is the tilt of the planet, so where that spin axis is pointing. And so the planet is rotating, it's spinning about this axis, and that actually changes. And that's what causes the climate cycling in the last 3 billion years of Mars. That's really dictated the Martian climate of recent being likely the last 3 billion years. And so that definitely has profound effects on the distribution of water on Mars, but it's mostly that's in the form of ice, and the water is going back and forth between being in the atmosphere and then settling wherever it's stable. And so if you can imagine you've got a planet that is just spinning with no obliquity, so the spin axis is pointing sort of straight up. The sunlight is coming in, and it's very direct at the equator, and so then all of the water ice is sort of locked up at the poles where it's cold, and it can't be stable at lower latitudes. But once you start getting that obliquity to be higher and higher, then all of a sudden where the sunlight is coming in and where it's the most direct is not at the equator anymore, but at higher latitudes. And so then you can actually get the higher latitudes, any ice that's there will sublimate directly into the atmosphere. It doesn't go through a liquid phase due to the pressures and temperatures, but it'll go into the atmosphere and then actually move and settle latitudes or even the equator if the obliquity is high enough, where high latitudes are getting the direct sunlight. And so you see this, like our concept of Mars climate change in the Amazonian periods of this last 3 billion years, since Mars has sort of undergone this drier, colder, drier climate, is that it's really dictated by this spin changing. And that's essentially what causes the seasons on Earth, is that we have a tilt. And so in different parts of your orbit throughout the year, that tilt is what causes the seasons. And so Mars is just undergoing these extreme changes because the tilt is changing. So on Earth, we have the moon. We have a big moon, and so that sort of stabilizes us. So we're barely changing from like our 23-degree obliquity. But on Mars, and this might be what you had been thinking about, is that people that have done modeling to try to come up with the orbital solutions of Mars, they can find solutions where Mars could have almost been at zero obliquity, or it could have actually been extremely high, 40, 50, maybe even higher obliquities. And so you just get really exaggerated seasons and climate change on Mars, and that causes this ice to move around and settle at whatever part of the planet is not getting the direct sunlight for that orbital solution.
Right. Yeah, Ali, thank you. I think that's exactly what I was thinking, had misremembered, that it does have this very wide, incredibly wide change in its obliquity. It does not, in fact, I am going to check Wikipedia.
Also,
you're right.
while you're at it, check
the,
so on Earth, to go, I believe, one full precession rate all the way around from the spin axis to go all the way around once is around 25,000 years. Do we have a sense of what that is on Mars?
Yes.
Yeah, John, do you want to answer that?
I'm not sure if I'm going to get the exact number.
Is it more or less than that usually?
More than that.
Okay, so it's a lot.
I think
longer.
it's like 100. I think it's like about 100,000 years or 120.
I think it's,
so for the spin axis to go a complete precession orbit or one complete turnaround is a lot longer than it is on Earth.
Not a lot.
But,
maybe a factor of 2 or 3.
Yeah, not a lot.
Well, 2 or 3 is, well, that's a lot. 100,000 years is a lot to me. But,
it's not a lot to physicists.
Yeah,
not a lot to geologists.
Or people who measure planetary lifetimes either. But
there's a couple different, because there's oscillations in the eccentricity, in the obliquity. So there's a couple different variables that are all oscillating.
So it sounds a lot more complicated on Mars than it is here on Earth, correct? I mean, it sounds to me like there's a lot of...
It's way simpler. It's a great laboratory to study climate change.
Okay, but are you saying that I don't want to get too much into this, but the angle of tilt is changing? Is that what you're saying? Because it's not really with Earth. I mean, it's staying.
But it still does a little bit. That actually are like glacial epochs and the ice ages on Earth are caused by even the small variations, within a fraction of a degree. The small obliquity changes. So imagine if Earth was wobbling as much as Mars does, if just a tiny fraction of a change in a degree in that tilt can cause the ice ages that, we know about on Earth. And,
that's what I'm trying to say. So on Mars, that is greater, much more pronounced. So on Earth, that seems to be in a much smaller effect than it is on the planet Mars. Did I hear that right?
Oh, I see what you're saying.
Yeah. Okay. So
but there's also less effects of you know, other effects. So it ends up being a great way for us to study what are the effects that orbital parameters have, and natural oscillations in orbital parameters. What are the natural effects of climate change from just orbital solution, like, you know, the obliquity changing, the eccentricity slightly changing, and that can actually allow us to then better understand the natural climate change cycles on Earth and be able to determine what is man-made climate change. And that's where Earth is a lot more complicated because of and
okay,
so
good.
So
Well,
it's a good laboratory for natural climate change and understanding the oscillations that happen naturally.
okay, good. Well, I just wanted to kind of verify, I would clarify some of that, because I was starting to get the sense that Mars is kind of moving all over the place. And of course, that would affect where water is on the surface of Mars. And this sort of brings me to a question I saw George Caldwell asking. Let me go back to it. Okay, so we're talking about, George, I'm going to ask your question right now. We're talking about the spin of Mars, the rotation rate, the precession of Mars on the spin axis, and obliquity, and all this other stuff. And of course, it's easy to picture how that would affect where the water is on the planet's surface and the distributing it. But Mars also is different from Earth in another very key way, and that is that Mars has a very weak, or not at all, very, very, very weak magnetic field. And so George Caldwell is asking, could the reason for water deserting Mars be due to it losing its magnetic field due to its small size and its core becoming inactive, meaning it would lose much of its atmosphere? Now, I don't know if there's a relation between a magneto and a the planet's core, which generates the magnetic field like on Earth, and an atmosphere, but maybe you could comment on that. Would water in any way be affected by the magnetic field on Mars, or the lack thereof?
Yeah, I can kind of answer that a little bit. So the loss processes that are occurring at the top of the atmosphere, in which you would lose water, it definitely occur at higher rates without a strong magnetic field to deflect energetic particles and things like that, which accelerate those loss processes. But there is still, I think it's a bit incorrect to say that Mars doesn't have its water, because there are two polar caps, and they're kilometers thick stacks of water ice that, if you were, say, to melt that ice, you could cover the planet entirely in water with roughly maybe a layer about 20 meters thick.
Really? That's a lot of water.
It's a lot of water.
A lot of water.
Yeah.
Okay, well, let's talk about that now that you brought up ice, and this is something you said you study at the top of the Hangout. You said you study these ice mounds. I want to get to those too. But there is a lot of water on Mars, just not necessarily a lot of liquid water. And so why don't you guys give us some sense of, well, you've already done that. There's enough water on Mars that we can see in the polar caps to completely cover the planet 20 feet deep. That's pretty amazing. So where is most of the water on Mars in ice form? And Ali, you want to try that, or should I give that to Jonathan?
Well, I think, you know, John just mentioned most of it is in the polar caps, but like something that I'm researching is trying to quantify how much is at lower latitudes, in the mid-latitudes, or even perhaps buried in the equator. We know that there's climate models that suggest that when you get these obliquity changes, you can actually get tropical mountain glaciers, is what they call them. And so you can get sort of ice deposits on the flanks of mountains near the equator. And so there's some evidence that suggests that maybe some of this ice is possibly still there today. And so that's part of what I'm researching, is trying to constrain the water ice abundance that's sort of buried underneath the surface at lower latitudes, to try to put get better estimates of the total water inventory on Mars. But in general,
how deep is this under the surface? How deep under the surface is it?
Oh, well, the mid-latitudes, the ice could be extremely close to the surface. Like, on the order of centimeters. So the HiRISE camera and the CTX camera, both on the Mars Reconnaissance Orbiter, have detected recent impacts. So we've taken a picture somewhere on the surface of Mars. Then we took another picture a couple months later, and there's a crater all of a sudden. And so we've been able to find new craters forming on Mars, and some of them in the mid-latitudes actually happen to hit into ice. And they expose and excavate ice. And so in the picture, we get this big, bright spot of water ice in the image, in the crater, and we can then keep imaging that same spot, and we watch the ice sublimate away into the atmosphere.
So hang on, you lost me. Where did that crater come from?
From an impact hitting the surface.
So something hitting. So something hitting the planet that was there. It was not there at some other previous time when you were imaging, and then in that crater, in the bottom of that crater, you see more ice forming.
So not ice forming, but ice that was there and exposed by this crater.
And John has a picture I've got up now of that. I see.
And Ali or John, does such impacts then, and the ice or the ice that's exposed, does that give you some information about how deep the ice might be found? That is, by making some estimate of how deep the impact was.
Yeah, so these craters that we're detecting are very small. They're on the order of a couple meters. It would be really unlikely to get a really, really large impact to hit now. Smaller impact or smaller meteorites and stuff are more common. And so these impacts, these craters that are forming are all really small. And so that suggests that this ice is within a meter of the surface, even perhaps on the order of centimeters or tens of centimeters. And so that suggests that there's ice that's actually really close to the surface.
Yeah, that's fascinating. Yeah.
Well, you said a few centimeters below in some cases. I mean, you could just walk by and just sort of sweep some sand away and there would be some ice there, it sounds like, right?
And that's what the Phoenix lander did. They were actually able to, they dug with their little scooper, and really close to the surface, they hit a layer of ice.
And you said these were in the mid-latitudes. Are these, and anybody can comment on this, I'm not, because I don't know for sure, are these some of the more advantageous places for us to land on Mars? So if we were to send human beings there, are these water ice pockets that you're finding underground pretty good spots to land?
I would think so. If, water is obviously an important resource. And so I would think, landing near the poles would be more difficult. And so the lower latitude you can land, the better. So trying to get to one of these lower sort of mid-latitude regions where there is, it seems like an abundance of water ice pretty near the surface would be, I think, an excellent place for human landing site selection.
Okay. Well, we're getting along, and I got a few other questions I want to get to, but Harley just pointed something out. So we recently learned, talking about Schiaparelli, the astronomer from the mid-18th or mid-19th century, who did these first canal drawings. There's a lander named after him, and I think, Harley, you wanted to ask about the ESA ExoMars mission that recently happened.
Yeah, we all, and of course, once again, our guests will know more about this. It was really disappointing. The lander appeared, well, no, the lander did crash. But what I wanted to ask our two guests were, as I understand the mission, the orbiter is functioning just fine. And in fact, the orbiter might have been the part of the mission that will produce the most exciting science results. Do I misapprehend that? Is it?
Well, no, yeah, it's designed to look for methane, I believe, primarily in the atmosphere.
Other things as well?
Well, signatures for life is what they're calling it. And I believe methane is the biggie, but are there others, guys?
Yeah, Jonathan, Ali?
I think, yeah, they wanted to find any sort of trace elements in the atmosphere, because it's called the Trace Gas Orbiter, and they wanted to find any evidence, mostly of methane, but other things that might be tied to life on Mars. And then the second part of that mission was the lander, sort of a pathfinder. They wanted to test the technology of landing for a future lander that they're building. They wanted to test it. Am I right on that, guys?
Yes.
Yeah, so I think the landing technology is going to be used in a couple of years for another lander. And so they probably will need to reevaluate and test that some more. But I think that lander was only going to take a couple of days worth of data. Obviously still very useful data that we're, going to miss. but the orbiter is really the primary, I think, component of the mission. With measuring the trace gases, especially methane, and also it's got a camera on board that's going to generate some amazing images. And it's also in, I believe it's in a different, so it might help us get more temporal coverage throughout, even looking at different processes throughout the day. Because the Mars Reconnaissance Orbiter is in a polar orbit such that we're only imaging at 3 p.m. And so I think the trace gas orbiter will allow us to get more images and more data from different times throughout the day. And
what Jon has up is a picture from HiRISE of the Schiaparelli landing site. Now, I know about this from doing this on Space Fan News, and I reported on this for that. But Jon, do you want to go ahead and describe what we're looking at?
Well, yeah, I mean, this just came out today, I'm pretty sure. I'm not even sure if it's publicly released. But anyways, this is just the color image
we don't care about embargoes.
of the crash site.
Right.
So yeah, on the bottom and the lower panel, I mean, you can see a scale bar there. So this is why you need a high resolution camera to image these things. And you can see the parachute on the bottom left.
And the heat disk as well, the heat shield.
Yeah, that might be on the bottom right. And then the above image is just kind of the zoomed out, I guess, a little bit.
So the thinking goes that the telemetry from the lander went, the landing firing rockets cut off very shortly after they started. And the thinking, I think, currently is that it was heading down at about 300 kilometers per hour when it hit, and one of the hydrazine tanks may have blown up on impact, which gave it that sort of skewed look on the spray pattern of the dark stuff that's there. But they're still investigating all of that. And like I said, it was designed to be a test bed for future landers that ESA was going to make to go that they're going to be building now. And as Ali said, they might want to have to look closely at some of that technology because it didn't seem to work the way I think they did. Obviously not the way they designed it, but there's been lots of other problems. So they're looking into that right now. Got a couple of comments here. Kilgore 757 is asking, when we say water, are we talking H2O or a version of a sort? In other words, could we drink this? What kind of water are we talking about? Is this like nice, fresh, cool, clean Mars water, or has it got stuff in it?
Yeah, I guess I can try and
go
answer
for
that.
It, Jon.
Yeah, so obviously, I mean, if the water is buried under soil in the form of ice, there's probably some kind of non-water particles or things like that. But in general, yeah, I think this water would totally be drinkable. I mean, you'd have to melt it, of course, a lot of this ice, but it's water.
Yeah, but it's going to be really cold.
Yeah, so you'd have to expend a decent amount of energy to melt it. But
it seems like there is a lot of evidence for salts near the surface of Mars as well, though. So definitely one aspect that there's a lot of research that's occurring on how much salts might be involved in the ice. But in general, the ice in the mid-latitudes, the radar evidence suggests that it's relatively pure water ice, but there might be some sort of there might be some dust mixed in, but likely not much. It's likely pretty pure. But
don't be wanting any dusty water. Get my dusty water cleared out.
Just filter it.
Yeah. Right. Get a Martian Brita filter. So Paul Roy is asking, it's a good question, actually. I'm going to get this one out. Would Mars have had a considerable greenhouse effect to stay warm at its distance from the sun? In other words, how did liquid water stay liquid for so long? This is going back up in Mars' geologic past when water presumably flowed by looking at all of these features that we see that might have been carved out by liquid water. So I guess the basic question is, how did liquid water, how was Mars different back then that allowed it to happen? Liquid water. Anybody?
I guess I'll try.
Well, we'd have to have more atmosphere, right? That's
Yeah.
almost
Yeah.
for sure.
Right. I think unfortunately the answer is we just don't know. People have been looking into this now for quite a while and testing different scenarios. So for example, one is to just kind of similar to Venus, not as extreme, but to just kind of load the atmosphere with lots of CO2 and create a very significant greenhouse effect. But there are other problems with that. And also some of the geologic consequences you would think of a large CO2 atmosphere would be obvious at the surface, which it really isn't. So it's not entirely certain how Mars could have sustained liquid water at the surface early on, and that's a hot topic.
And one of the big parts of the problem to explaining this also is that the sun, so like 4 billion years ago in the Noachian era is when we see a lot of the evidence, these geomorphic features for abundant liquid water. But 4 billion years ago, the sun actually would have been like 25 or 30% less bright then. So that adds to this problem is this faint young sun paradox, is that 4 billion years ago, the sun actually would have been less bright. And so you would expect that all the planets would be a little bit cooler. And so that means you really have to get a thicker atmosphere or something to contribute to a greenhouse effect to try to offset the fact that the planet's also naturally going to be cooler due to a fainter sun. And so I think some people have also tried to load the atmosphere with some sulfur dioxide, maybe from volcanic outgassing. That's been suggested as a possible mechanism to invoke this greenhouse gas effect in early Mars. And another hypothesis that's maybe less dependent on the greenhouse effect is if when you had more impacts and bigger impacts happening earlier in Mars's history, perhaps big impact events would actually generate the energy needed to have a thermal environment where you could get a lot of liquid water temporarily flowing to create those features. And so the big question I think that the field is trying to work on right now is would we expect greenhouse gases and sort of Mars to be very warm and wet for an extended period of time? Or is the liquid water, where the liquid water could have sort of existed for a while, or was the liquid water very much a temporary, just spontaneous thing due to isolated events, and that's what caused all the features that we see today? That's the big question that I think we all sort of want to get at if we want to understand Mars's history and liquid water.
Yeah, it's amazing. The more we send to Mars, the more we learn about it, the more rovers we have driving around, the more orbiters we put up around it. It still seems like we've got a lot of questions left to answer for the red planet. So let me go to something. Galaxia is back. Hi, Galaxia. She's asking, how long did it take for a couple of centimeters of dust to form over the ice? So you were talking about this layer of dust over the ice. How long does that take to form? We all know, or at least we've heard about these dust storms that happen over the large portions of the planet. So is this a long process? How long does that take? Anybody? Ali?
I mean,
you were talking about subsurface ice.
Yeah, it sort of depends, but in general, because of the recent impacts that we found and the fact that we can see them fade, they're fading because that ice is sublimating into the atmosphere and leaving behind its dust, and so it's sort of it's turning into just what looks like the rest of the dust nearby. So it seems like it should be a relatively fast process, that as the ice that has a little bit of dust content in it, the ice leaves or sublimates into the atmosphere, and it leaves behind any dust particles that were in it, and that can build up. But we're not. I don't know that we know exactly how long it takes, but at least with these ice exposing impacts, it can happen. At least you can get a fine layer of sort of regolith covering pretty quickly, but we're not sure how fast that builds up.
Okay, great.
And how thick, but that's something, that I'm looking at right now.
Okay, good. Well, let us know how that turns out.
Yeah, exactly. We'll have her back.
That's right. So,
I mean, come on, what's with this? Drop us an email.
You had this whole hangout here to get this done. So I don't get the problem here. So Paul Roy is clarifying on the live chat. He says that ESA's TGO is looking for trace gases, methane, I think, and that of course is one of them, and hope to be able to determine if it's biological or geological in origin. And that's a good distinction. That they are trying to look at these trace gases in the atmosphere and see what could have caused them. Hopefully, we're all hoping there's some kind of life, or at least some people are hoping. I'm not necessarily rooting for life on Mars, but that's a topic for another hangout. But so yeah, okay, good. So thank you, Paul Roy. I appreciate that. Do we know what's next for Mars? What other rovers, spacecraft? I mean, we just had ExoMars get there. What's coming down the pike?
Yeah, I think at least so every 10 years, the planetary science community will put together this document called a decadal survey that kind of prioritizes science goals for the space program. And the most recent one of those documents put Mars sample return at the highest priority. So
really, so go there, get something, and bring it back.
Yeah, well, it's definitely complicated. It's one of these multi-mission types of proposals, because you'd have to send a caching rover to basically get the sample, then another mission to take the sample and put it into Mars orbit, and then maybe another mission to bring it from Mars orbit back to Earth.
So it's not very straightforward. And OSIRIS-REx is trying to do that right now with an asteroid. So
right, it's much easier to do with an asteroid.
Mission.
Yeah, and it's a lot simpler too. It's going down, it's going to go blow up some sand, grab it, and then run back and send it back. So yeah, it's a little bit more involved. So the Mars sample return mission, that's great. So the decadal surveys, we've talked about them many times in the astronomy community, cosmology especially. They come up with things like the Hubble Space Telescope came out of one, James Webb Space Telescope, which is being launched next in a year, October 2018. That came out of a decadal survey. WFIRST is another one. So these are things that planetary science scientists do as well. And so any rough idea when that might happen?
Well, the first step is the Mars 2020 rover. So as the name suggests, the plan is for it to happen in 2020, so pretty soon. And the goal is for it to actually cache, to be caching samples. So as it roves around, it can collect samples and hold on to them, and that might be sort of step one of that sample return proposal that Jon mentioned.
Yeah, that sounds pretty complicated, all those different phases. But and of course, we know that NASA has got, not in the rover land, but in actual getting people to Mars land, the 2030s is the time scale for that. And unless Elon Musk or somebody else comes along and decides they're going to do it quicker, but we've talked about that in past hangouts before, so we'll see how that plays out. Harley, did I get to everything? Do you have any other questions you want to ask?
No, I think we did. We did really well.
Yes. Okay. Well, thank you. All right. Well, I want to thank you guys for taking time out to talk with us. Jonathan Bapst and Ali Bramson, both from the University of Arizona, taking time out. I got to know, will you come back in our hangouts after you defend your thesis and talk about it?
Absolutely.
Yeah.
Awesome.
Actually, that would be a lot of fun. We have, and Ali has already said that once she completes her analysis, she will come back and report at the same promise from Jonathan.
Yeah, you didn't know you were going to get homework on these hangouts, did you? But then you're used to it as PhD students, I'm sure. All right. Well, thank you both very much for taking time out to talk with us about water on Mars. We want to thank all of you guys for watching. We'll be back next month. Harley, do you have a preview for us, or are we still working?
We don't have a preview. We are negotiating with a couple of different topics, both of which are terrific.
Okay, well, stay tuned. The best way to find out about these hangouts is to follow me on Twitter at DeepAstronomy. I tweet about them all the time. Also, if you sign up to the newsletter on DeepAstronomy.com, I will send out announcements and alerts that way. Also on Facebook at Deep Astronomy, facebook.com/deepastronomy, and I post on there as well. So that's the best way to find out about future hangouts. Next week, we have a we're back to doing Astro Coffees. I'll be joined by my co-host Carol Christian, and we're going to be looking at gamma ray emitting binary star systems. There's some latest research to come out that has shown that these are the very first gamma ray binary star systems that they've seen in another galaxy, and we're going to talk about what those are like next week, November 10th. So we hope you'll join us then. So, okay, well, I guess we'll call it a hangout this time, guys. I want to thank all of you for watching. Thank you all for taking time out to comment also and to interact with us. We do appreciate it, and we'll see you guys next week. On behalf of
We forgot the duck.
on behalf of our Mars water riding to rubber ducky.
Yes.
We got to come up with a name for this guy. As well as Jonathan Bapst and Ali Bramson. Thank you both very much. Thank you all for watching, and as always, keep looking up.